Okay, it's our second lesson for Unit 3. We're still talking about solving systems, but this time we're going to talk about how to solve systems using a different method, so without actually graphing, because we can't always have a graph in front of us, and some lines are just really tough to graph, and so we want to have a different method other than graphing on how to solve these linear systems, so how to find solutions to a system by using a method called substitution. Okay, so for a warm-up, we're going to actually link it back to yesterday's lesson. So here are two equations. So here's our system, but notice in each of the equations we are missing a value. So that big capital A is a placeholder for one value, and the big capital B is a placeholder for a different value. And so part 1 says, what values of A and B would make the system have no solution? So what numbers would we put into those spots for A and B that would make the system be a no solution system? And then number 2 is, what values for A and B would make the system have infinite solutions? So pause your video and see if you can figure that out. So yesterday, when we talked about our systems and we were solving by graphing, any system that had no solution really meant that those two lines were not intersecting, right? Because the solution is the point where the two lines intersect. So no solution really meant that we had parallel lines. And if we remember, for parallel lines, that meant that we had the same slope but different y-intercepts. So if I look at my system here, the placeholder for A, that's in the slope position for that first line, right? So y equals mx plus b, that A is in the m spot for my first line. And so if I look at my second line, the slope of the second line is 2. So if this is going to create parallel lines, the slopes have to be the same. So A must equal 2. And we said that the y-intercepts had to be different. And I noticed that the big capital B is a placeholder for the y-intercept in the second line. And so since the y-intercept for the first line is 9, my y-intercept for the second line has to be something else. So we could say 27 if we want to. But really, the idea is that you could put any number in here. Actually, I should say that. Any number other than 9, right? But it does say what value, so we actually have to give a value here, but any number other than 9 would work. 1,972 if you really wanted to. Okay, now the second part says what values for A and B would make the system have infinite solutions. So if we remember from yesterday, infinite solutions, that was when we had the same or overlapping lines, right? And if I'm going to have the same line, that means the equations have to be exactly the same. So that would be same slope and same y-intercept. So if I look at A in this case, it has to be the same again, right? So A will also have to equal 2 on this one, but this time my y-intercept has to also be the same. So B has to equal 9 on this one so that the two equations are identical, and that would give me those overlapping lines, which would give me infinite solutions. All right, so hopefully you remembered that from yesterday or looked it up along the way if you didn't remember. So now we're thinking, how do I solve this system, right? And remember that last one we really reviewed that the solution to a system is the point, x comma y, the point where the two lines intersect. But I don't always want to have to graph the lines. For example, on these two equations, y equals 35. That's a huge graph, right? And x plus y equals 50. If I subtract x from both sides, that means my y-intercept is 50. That's a huge graph. I don't want to have to do that. So I want to have a different way. Now, hopefully there's something that's jumping out at you right away. You see in this top equation, it says that y equals 35. And there's a y in the second equation. So I should just be able to take that 35 and substitute it in for y in the bottom equation, right? Since I know what y equals already, let's just plug that number in. So then my equation becomes x plus 35 equals 50 on my bottom equation. Oh, well, that's an equation I can solve. So I subtract 35 on both sides, and I get x equals 15. Oh, well, now remember my solution is the point x comma y, right? Well, I just found that x equals 15. Sorry, my pen stopped working. There we go. X equals 15, and my top equation said that y equals 35, and there is the point really easily without having to graph anything, right? Now, that was a very basic one. They don't usually give you y equals a number. We don't have a lot of horizontal lines showing up in our systems, but sometimes you do, and then it is that easy, right? But sometimes they're more complicated, but this one really introduces the idea of substitution. When we have something that says y equals or x equals, I just take whatever it equals and I plug it into the other equation for that variable. That's called substitution. All right, so let's take a look at one that's just a little bit more complicated. This time I have y equals 3x plus 2, and x plus 2y equals 11 as my two equations for my system. Now you'll notice in this one, just like in the last one, I have y equals, right? So I have this y by itself. Now in this case, it doesn't just equal 35. It equals this whole thing, 3x plus 2. But I can still take that whole thing and substitute it in for the y in my other equation. Now be careful on this one. On my other equation, then I have x plus 2, and then the y is written right next to it, so that really means x plus 2 parentheses 3x plus 2, right? I need to take that whole, whatever y is, and I need to multiply all of it by 2, so make sure that we use the parentheses when we're substituting with more than a single number like that. Okay, so I've got x plus 2, parentheses, 3x plus 2 equals 11. So we just took that 3x plus 2, that y equals, and I plugged it in for the y in my other equation. Now notice, in both of these equations, when I plugged it in for y, there is no more y in my equation. So after you substitute, you should be down to only a single variable, right? There's only x's left. If you substitute in and you still have both variables, if you still have an x and a y, you've done something wrong because you can't solve one single equation for two variables. It doesn't work. So this is the whole process, is to get rid of one of your variables. So make sure that after you substitute, you're only left with one kind of variable, only x's or only y's. Okay, so let's get to solving now. Now, hopefully you're looking at this going, yeah, I know how to solve it from here. I'm going to distribute my 2, so I have x plus 6x plus 4 equals 11. I'm going to combine my like terms here, so I get 7x plus 4 equals 11. Subtract 4, so I get 7x equals 7, and divide both sides by 7, so I get x equals 1. Now remember, our solution to a system is always the point x comma y. Now I just solved for x. I got x equals 1. Now in the last problem, I already knew what y equaled. It gave it to me right in the equation, right? And this one, I don't know that. But I do have this top equation that says y equals 3x plus 2. So I can now, but I know that x equals 1 now. So I'm going to take that top equation again, and I'm going to plug in that x equals 1. So I'll have y equals 3 times 1 plus 2. And I can solve for y. Oops, I meant to change back to red. There we go. Okay, so after I solve for one of the variables, I'm going to take that number and plug it in to one of the equations and solve for the other one. Now, I picked the top equation because it was all set up nice for me. But you can plug it into either equation because remember, this point has to be two values that work in both equations. So it does not matter which equation you plug back into. If we wanted to take that x equals 1 and plug it into the bottom equation to solve for y, you sure could, and you would get the same number because it's the point that works in both equations. All right, so let's finish solving it out here and figure out what our y actually is. So 3 times 1 is 3. So y equals 3 plus 2, so y equals 5. So my solution is the point 1, 5. All right, so on that one, whenever we have more than just a number, it still works. Whenever you have an x equals or a y equals, we take whatever it equals and we substitute it in for that variable in the other equation. Be careful that you're putting it in parentheses if it's more than a single number. Okay, so here's our next equation. Now I have x minus 2y equals negative 6, and I have negative x plus 6y equals 18. Now the problem in this one is I don't have an equation that says y equals or x equals already. Now here's my hint. If we're going to use substitution, I want to make sure that I don't ever end up with fractions. If you're moving things around and you end up with a fraction in your equation, it is going to be way too complicated to solve the system that way. So don't do it. You go back and try something else. My other hint for you is this. You should be able to get an x or a y by itself in one step. So look for the equation where you could just move one thing and you'd have an x or a y by itself. So if I look at this one, I'm going to take a look at that top equation. You know what? That was too dark. I apologize. You couldn't really see it anymore. So right here, this guy. And I see that x is very close to being alone. All I have to do is add 2y to both sides, and then my x will be completely by itself. My equation will become x equals 2y minus 6, or negative 6 plus 2y, however you want to write it. And now you'll notice that I have x equals. Now in the last two problems I had y equals, but it works with x equals as well, as long as you have one variable all by itself on the one side of the equal sign. X equals 2y minus 6. So I'm going to take that 2y minus 6 and I'm going to plug it in for x in my other equation. Make sure you move to the other equation when you plug it in. Now be careful on this one. I have that negative sign out front. And then I'm going to have my parentheses with the 2y minus 6 inside. And then it's going to say plus 6y equals 18. Notice all that I replaced was the x. The negative stayed, the plus 6y equals 18 stayed, and I put that 2y minus 6 in parentheses. But I'm substituting in for x this time because I got the x equals, right? So make sure you're substituting in for the correct variable. That's kind of what I'm talking about. If you accidentally plugged it in for the y, you would still have an x in the equation, and now you'd have a y in the equation as well, and then something went wrong. So make sure that you only have a single variable or one kind of variable left, y's only, after you substitute in. Okay, now we're going to keep on solving. Remember, this negative sign is really that invisible 1, so it's negative 1 that I'm going to distribute to both things in my parentheses. So I have negative 2y plus 6 plus 6y equals 18. Combine my like terms. I get 4y plus 6 equals 18. I'm going to subtract 6. I'm going to get 4y equals 12. And then I divide by 4. And I get y equals 3. Now be careful this time. I found y equals 3. So make sure you put that 3 in the y position in your coordinate. Now I need to solve for the x. Again, you could plug that y equals 3 into either one of your equations, but I think that that top one is all set up nice and easy for me, so I'm going to go with that equation to plug into. So I now have x equals 2. Instead of y, I know that the y is 3, so it would be 2 times 3 minus 6 to figure out what my x value is. So 2y minus 6, but I'm plugging in the 3 for the y. So x equals 6 minus 6. 6 minus 6 is 0, so x equals 0. Now remember, 0 is a number. Can you picture that point on a graph, the point 0, 3? Sure, that's 0 left and right, 3 up. That's a point on the graph, so don't be afraid when you get 0 as an answer. 0 is still on the graph. Don't worry about it. Okay, so if you have a system that doesn't have an x equals or a y equals to start with, you should be able to move one thing and get that x or y by itself. If you're trying to move 2 or 3 things, or you end up with a fraction in your answer, there is an easier way to go about it. Try a new way. Look for something else that will be an easier way to get an x or y by itself. All right, why don't you try this one on your own? See if you can get an x or y by itself in one step. and then substitute in. Go ahead and pause your video. All right, when I look at it, I see this top equation jumping out at me that all I need to do to get that y by itself is to subtract 2x on both sides. And so then that means I get y equals negative 2x minus 2. Or it could be y equals negative 2 minus 2x. I just have that slope-intercept form ingrained in my head. So now I have the y by itself. So y equals negative 2x minus 2. So I'm taking that negative 2x minus 2, and I'm going to plug it in for y in my other equation. So I'll have 4x plus 2 parentheses negative 2x minus 2 equals negative 4. So I'm plugging in that negative 2x minus 2 in for y. All right, now I'm going to distribute my 2 on this one. I get 4x minus 4x minus 4 equals negative 4. Oh my gosh, we have so many 4s. Wow, okay, so I'm going to combine my like terms here. Wait a second. 4x minus 4x. That cancels out. That gives me 0, right? I don't want to write an x anymore. I got no x's left. They're all gone. What I'm left with is negative 4 equals negative 4. Oh, well, we're used to seeing equations like this. When I get negative 4 equals negative 4, that means that I have infinite solutions. Oh, yeah, remember back to yesterday, we can have systems that have infinite solutions. Those would be my overlapping lines, right? Or the same line. Wait a second, look back at those equations. Hey, if I just multiply that top equation, everything by 2, it would match the bottom equation exactly. These are overlapping lines. But this is what it would look like when you show the work using algebra rather than showing the work on the graph. It still can have infinite solutions. Now think about what the system would look like if it had no solution. Instead of getting negative 4 equals negative 4, I might get 8 equals negative 4. That would be a no solution, right? When you look at your equations, you would notice that they'd have the same slope, but the different y-intercept. Now, these aren't always set up in that nice slope-intercept form, so it's not always obvious. And so then you need the algebra to give you those answers for infinite or no solutions. So be watching out for those today, too. Infinite and no solutions can definitely pop up, but you should recognize them when they happen. Okay. Now, the last thing is, okay, we have these systems, but when do you use them? I tell you, man, systems are the thing that you will use. So many times you guys ask us, when am I ever going to use this in my real life? And I will tell you that systems is something that will pop up in so many of your careers out there. There is just so many times when there's two different things that you have changing in a situation where you need to figure out when it balances out or when one is better than the other. And so systems are things that pop up all the time. So here's an example for you. Heather and Meg are selling boxes of candy for a fundraiser. Together they sell a total of 86 boxes. Heather sells 10 less than twice as many boxes as Meg. How many boxes did each of them sell? So remember, whenever we're writing, whenever we have a word problem, we always want to start by defining our variables. What are we trying to find? What don't we know? So we're trying to find how many boxes each of them sold. And by each of them, we mean Heather and Meg, right? So why don't we use, now you could use X and Y if you want to. I'm going to use H for Heather. H equals the number of boxes Heather sold. Notice I'm not just saying Heather. H equals Heather. I want it to be more clear. What about it? It's the number of boxes, right? And M equals the number of boxes Meg sold. Okay, now I'm going to go through and I am going to find my sentences in my equation that are in my problem that will help me write some equations. Remember, I have two variables, so I have to write two equations. So here it says, together they sell a total of 86 boxes. So total would mean that I need to add the number that Heather sold to the number that Meg sold, and it's going to equal 86, right? So the total number of boxes, the number of boxes Heather sold, which is H, plus the number of boxes Meg sold, which is M, equals 86. Now it says Heather sells 10 less than twice as many boxes as Meg. So let's see, the number that Heather sold is 10 less than twice as many boxes as Meg. So I'm going to do the twice as many boxes as Meg and subtract 10 from it, right? Less than, I need to make sure that I switch the order here. So 2m minus 10, not 10 minus 2m, so be careful. All right, now I have my two equations. Hey, look at that. It's set up perfectly for substitution. I have h equals, so I'm going to take that 2m minus 10, excuse me. I'm going to take that 2m minus 10. I'm going to plug it in for h in my other equation. So I'm going to have 2m minus 10 plus m equals 86. All right, combine my like terms here. I have 3m minus 10 equals 86. I am going to add 10 to both sides. I have 3m equals 96. I am going to divide both sides by 3. And I get m equals 32. Now let's remember again. Let's see. M is the number of boxes Meg sold. So Meg, sorry, I lost my pen. There we go. Meg sold 32 boxes. But that's only half the story. I need to find how many both of them sold. So I'm going to go back to my bottom equation here, and I am going to plug in right here. So h equals 2 times 32, because I know how many Meg sold now, minus 10. So let's see. H equals 64 minus 10. So h equals 54. So Heather sold 54 boxes. And now I have my answer. So there's a little real life situation for you on how to do that. Now don't forget to make sure that you define your variables. That's important when we have two of them for sure. So to wrap it up, remember the solution to a system is the point x comma y. We always write our solutions as points, unless of course we're dealing in a real world situation like that last problem. When we're using substitution, look for an x equals or a y equals in one of the equations and substitute into the other equation. If you don't have x equals or y equals, you should be able to isolate one of those variables in one step. So if it takes you more than one step or you end up with fractions, go back, look for an easier way. And then if you, when you have word problems, don't forget to define your variables. All right, good luck substituting.